Hello and welcome to the first part of my 10-part seminar series on multivariate statistical analysis. For today's presentation, I will be taking you through a general introduction of multivariate analysis and also perform a R demonstration of the simplest form of multivariate analysis, which is mean comparison. So what is multivariate analysis? Well, some of you, I'm sure that when I say multivariate analysis, you might be thinking of something like this right here. You have a outcome and you're trying to see what is the effect of several variables and how it influences this one outcome. But this is actually a form of univariate analysis because there is only one outcome. A multivariate analysis is different because we have several outcomes and we are trying to see variables and their effects on several outcomes simultaneously. So to give you an example, let's say we had a free breakfast program for school children. So we're trying to see what's the effect of this program on the school children in terms of their grades, their behavior, and their absence from school. And we're trying to compare the effect of this program on children with high and low socioeconomic status. So this is a situation where we would use a multivariate analysis rather than a univariate analysis such as this one. So this is the objective list of what I'm going to accomplish for this presentation. So first, we will go through assumptions. So multivariate analysis, like univariate analysis, we also have to meet certain assumptions before we can proceed with the multivariate analysis. Next, we're going to discuss some issues that's going to make a difference in the results of the multivariate analysis. After that, we get into the R demonstration where I will be performing a mean comparison test. We have the Halflings Tsquare test, which is the multivariate analysis equivalent of the univariate analysis version of the t-test. After that's done, we're going to discuss why we should choose multivariate analysis over univariate analysis for some of our studies. And at the end, we will discuss some future presentations that I'm going to give. Like I said, this is a 10-part seminar series, and this one is just the first part. So there are three assumptions that we must meet in order to proceed with the multivariate analysis. And the three assumptions are normality, and also the determinant of the variance-covariance matrix must be positive for the data set. And the third one is the variance-covariance matrices of the two groups that we're going to be comparing must be the same. So for the assumption of normality, it means that all the outcome variables that we must look at for the analysis, they all must have normal distributions. So in order to test this assumption, we can use the Shapiro-Wilk test. Now, the Shapiro-Wilk test, it will test whether or not one or more variables of the multiple outcome variables, if they are non-normal, and if we want to figure out which variable is non-normal amongst the several outcome variables, we can use one of these 5 tests in order to find the culprit. The second assumption that we must test is that the determinant of the variance-covariance matrix must be positive. So a variance-covariance matrix would look something like this. So in the diagonal line, we have the variances of the outcome variables. And the rest of the spots, we have the covariates of each of the pairs that's possible within all the outcome variables. Now, the determinant of the variance-covariance matrix, it's important because it indicates the amount of variance that are in the variables, and also the determinant of the variance-covariance matrix, it's very widely used in multivariate analysis, so it's important that it is positive, and we will get to this more later in the other seminars in this series. And the third assumption that we must test is of course, it's the equality of the variance-covariance matrices. So I'm going to describe this with an example. So for the previous example of the free breakfast program, we are trying to compare students, how the program affects the students when the students are in higher socioeconomic status group or lower socioeconomic status group. Now, in this case, the students from the higher socioeconomic status group and the lower socioeconomic status group, they must have equal variance-covariance matrices in order for us to proceed with the multivariate analysis. And for this testing of assumptions, it can be done by performing a test. It's called the box M test right here. Now, as for issues, sometimes there are issues that could happen which could interfere with the results of the multivariate analysis. So when it comes to outcomes, we can have infinite amount of outcomes, but the thing is, the higher number of outcomes that we have, the more likely it is that we are going to have correlations between the outcome variables. And this problem, it is solvable by keeping the number of outcomes to be lower than 5. Now, the correlation amongst the outcomes, it's a problem because it's difficult for us to see how the variance of each of the outcome variables are distributed amongst the outcomes if there are too many variables. And as for the independent variables in question, multicollinearity is a big issue because the more the variables are, the more multicollinearity there is amongst the variables, the more difficult it is for us to see how these variables influence the outcome variables. And for this presentation, I will focus on the correlation here. There are other issues here as well, but they're more applicable to situations in the future seminars. So I will only be discussing the correlation for now. So the simplest form of multivariate analysis is the Hotlinks Tsquare test. Now, Hotlinks Tsquare test is similar to the t-test in the univariate analysis case. So let's just have a quick review of the univariate t-test. So for the t-test, we have a situation where we are trying to compare the means of two groups for a single variable. Let's say if we have an outcome variable that's represented by the letter y, and we are trying to compare the means of two groups, we would have two means. To see if their differences are statistically significant, we would calculate this t-value like this, and then we would take this t-value and look it up at the t-table so that we can see whether or not the differences between the two means are significant. But for the multivariate analysis, we are not trying to compare two means that are just two numbers. We are trying to compare two means that are two mean vectors. So in the multivariate case, we have several outcomes. Let's say in this case we have three outcomes. That is y1, y2, and y3, and we have the same right here. And we are trying to compare the means of each of these three variables together between two groups, and in this case I used females and males as an example. But since we are trying to compare mean vectors instead of just mean numbers, we cannot use the t-table to test the hypothesis. So to solve this problem, instead of calculating the t, we calculated the t-squared value so that we can later manipulate this number to change it into an f value so that we can use the f table to test our hypothesis. So to change the t-square value to an f value, we need to multiply it by a number, by a fraction, and this fraction, the numerator, is the number of the dependents that we're trying to test. So in the previous example, it's the number 3. For the denominator, we add the number of people in group 1 and the number of people in group 2 minus the number of the dependents in question, which is 3, following the previous example, and minus 1. And we have the f value. There are 3 types of Hotlinks t-square tests. The first one, we test to see if the mean from the sample, whether it's too different from a mean that we have set up. The second one is the 2 independent group means. So we're trying to test the means of 2 groups that are independent. And the third one is called the 2 groups paired dependent variable mean test. So for the R demonstration, I will only be performing the 2 independent group means test because this one is most relevant in epidemiology. For the R demonstration, I will be using the Chatterjee price attitude data. This data was collected from 3 employees from a financial organization. And this data set, it contains about 6 variables, or 7. And for my demonstration, I will be only looking at these 3 variables. And for the variable complaint, this variable it measures the 30 employees' opinions on how the company handled the employees' complaints. The learning variable, it describes how the 30 employees, what was their attitude towards the company's how the company offered opportunities for them to receive training so that they can be better at their jobs. The variable raises is the employees' attitude towards how the employees received raises based on their work performance. So this is the hypothesis that's going to be tested for the R demonstration that I'm going to perform. So the null hypothesis in this case is that the females' attitudes measured using these 3 variables, complaint, learning, and what was the other one, raises? how the females' attitude towards their job compared to the males, and for the null, their attitudes are equal. But for the alternative, the females, their attitude towards their job, measured by these three variables, are different from the males. So, to demonstrate the process of how to perform this Hotlinks T-square test, I need my RStudio software. And I have the code prepared right here. So doing a multivariate analysis, it's very similar from doing any other type of analysis using a statistical software like RStudio, that is. And first, of course, we need to read the dataset attitude into the environment of RStudio. But for RStudio, the dataset is already built inside the IDE itself. So all I have to do is attach the dataset into the environment so that I can access it. So if I were to run this line right here, it attaches the dataset into the environment. But like I mentioned, the attitude dataset, I only need 3 variables to do this demonstration. So what I do here is I take the 3 variables in the attitude dataset and I put them into a data frame and assign this data frame to the name of attitude. I can do it by running this line. Now, what I did here was that I just put my cursor right here, then I do Control Enter to run this line itself. But you guys can also highlight the line that you want to run and push this run button here. It will perform the same thing. So as you see, I attached the data set, I read the variables that I want into a data frame and assigned it to the name of attitude. So after I do this, the data set is read into the environment. So as long as I click here, I can see the data set that's here. So now we get to the part where we test for the assumptions. Like I said, before we move into the analysis, we must make sure that all the assumptions, the criteria are met. So in order for us to test for the normality of the variables, these 3 variables here, I like to use the Shapiro-Wilk test. There are other tests available also, but the Shapiro-Wilk test is the best one. So as a software, it's really just a programming language. So what we do is we use the R language to write a program so that it can perform statistical analysis for us. But if we have to write a program every single time in order to analyze our data, it's probably going to take the rest of our natural lives. Which is why that there are plenty of built-in functions in R, and there are also some R packages that contains all the functions that are used to perform data analysis for us that are written by some very smart people. So for the Shapiro-Wilk test, we perform using a function. It's called the Shapiro.test function, and this function is contained in a package. It's called Multivariate norm test. So first, in order to access this function in this package, we must first install this package into RStudio. And it's going to take a little while here for the package to install itself. There we go. So now we use the library function in order to be able to access the functions in this package. So we run this library function, and even though there's a warning message, but it's okay, it's properly performed, this function. And now we can actually perform the Shapiro-Wilk test. Now, this function, it doesn't take the attitude dataset itself. We can't just use the attitude dataset itself for this function. We must first transpose this dataset. Now, this doesn't happen for every R function. This is just a situation where this function here was just designed to only take transposed datasets. So we first transpose the attitude dataset, and we see the name transpose attitude, and we can open it. And as you can see now, the variable names are all on the left side, and the data are arranged like this. But in the original dataset, it's like this. So the data itself was not changed, it's just transposed. So now we can perform this Shapiro-Wilk test. And you can see here that the p-value is 0.057. Now, for the Shapiro-Wilk test, the null hypothesis is that all of these three variables are normal. Okay? So this p-value, it's not lower than 0.05. So we cannot reject the null hypothesis that all of these variables are normal. So in this case, the normality test, this dataset passes the normality test for all the variables. Next step, we should test whether or not the determinant of the variance-covariance matrix for this dataset, whether it is positive or not. In this case, we have a built-in function called cov. And this function, if we put the attitude dataset, don't have to transpose it, just put it right in, and we will get the variance-covariance matrix of the attitude dataset. So we just run this line right here. And then we use the determinant function in order to get the determinant for this variance-covariance matrix. And as you can see here, the determinant is very positive. So this dataset passes the positive determinant test for the variance-covariance matrix. Now let's test for the third assumption, that the variance-covariance matrices for the groups that are being tested, whether or not they have relatively equal variance-covariance matrices. Now, as you can see from this dataset, we don't have a variable that shows which individual belongs to which group. So what I did was that I created a group variable in the form of a vector where the first 15 individuals are males and the last 15 individuals are females. So as you can see here, the group variable, the first 15 individuals are males and the last 15 individuals are females. And since there are only 30 individuals in this data set, we have two groups for the people in this data set. And so the next step, we use the box M test in order to see if the males in the group and the females in the group have relatively similar variance-covariance matrices. And this box M test function, it belongs in the R package, which is called BioTools. So we, like before, we install this package and we use the library function so that we can access the functions in this package. And then we use the box M function, and this function takes two things: the attitude dataset and also the group variable, so that we can perform this test. Now the box M test, the null hypothesis for this test is that for the two groups, the males and the females, the variance-covariance matrices, they should be the same. And in this case, the p-value is 0.06. So again, we cannot reject the hypothesis that the males and females have relatively similar, at least not significantly different at the statistical level for their variance and variance-covariance matrices. Okay, now that this data set, we can see that it passes all the assumption tests. We can now get into the Halflings Tsquare test, where we compare the two independent group means for males and females. So before I want to do this test, I like to see the means of each of these three variables individually. And there is an R package that can help me do that. This package, gplots, it contains a plot means function that helps me plot the means of these variables right here. So like before, I need to first install these packages, use the library function so that we can access the functions. And I can just run this code that I wrote right here. So as we can see here, that for the complaints variable, this score is the mean that represents the male's attitude towards their job in terms of how their complaints were handled, and this is for the females. And as you can see, these values, they're pretty similar. And then we do the same thing for the variable learning. And we can see here that this is the male's attitude in the 30 people who were in the sample. This score represents the mean for their attitude towards the company's offered training programs. This is for the males, and this is for the females. And we do the same thing for the raises. So right here, this is the mean that represents the male's attitude towards the amount of raises that they received based on their job performance. And this here, it represents the female's attitude in terms of the raises that they received based on their job performance. As you can see, that some of these scores, they can be quite different, but are they really that different at the statistical level? In order to determine that, we need to perform the Hotlinks Tsquare test. And the Hotlinks Tsquare test function, it's located in a R package that's called ICSMP. And in order to access this function, we need to first install the package. and then use the library function so that we can access the packages we can access the functions that are in this package. And this Hotlinks Tsquare test, it takes in two things. It takes the part of the data set that takes the first 15 individuals and the part of the attitude data set that takes in the last 15 individuals. So we have 1 to 15 here, and these 15 are the males, and this is the last 15 people from 16 to 30. This represents the females. So we perform the Hotlinks Tsquare test, and there is our p-value. Now, the null hypothesis for the Hotlinks Tsquare test is that the males and the females should have relatively the same attitude towards their jobs based on the measurement of their raises, the learning, their attitude towards the training programs that the company offers, and how their complaints were handled by the companies. And in this case, the p-value is above 0.05, so we cannot reject the null hypothesis that the males and females have the same attitude towards their jobs. So that is our result based on this data set. Okay, so now that we are done with our demonstration, some of you might ask me, why is it that we should choose multivariate analysis over univariate analysis? Because for multivariate analysis, we are trying to compare the means of several variables between two groups at the same time. But which it seems like it can also be done with univariate analysis by comparing the variables for two different groups, one at a time. So multivariate analysis does seem to be a little bit more complicated. Why not just stick to what we know with the univariate analysis? The answer to this question is that sometimes when we have a study and we have a treatment that was imposed onto the population, this treatment might affect the individuals in many ways, in more than one way. So if we want to see a bigger picture of how a treatment affects the individuals in a population, we need to see several outcomes and how they're affected at the same time to get a bigger picture. Also, at the same time, multivariate analysis can keep the type 1 error level to a low place, because when we compare three outcomes together for different groups, we can keep the type 1 error. Let's say we want a type 1 error at the 0.05 level. To compare three outcomes, the means of the three outcomes at the same time, we can keep the type 1 error at 0.05. But if we were to compare the means of each of these three variables one at a time, so for the variable complaints, if we compare the complaints from the females and the males together at one time, that's 0.05%. If we do the same thing with the learning variable and the raises variable, each of them is 0.05 type 1 error. And if we were to take all of these univariate comparisons and use them to arrive to a conclusion for the bigger picture, the type 1 error level is not going to remain at 0.05%. It's going to go to a place where it's around 0.15%. Well, not 0.15%, sorry, it's around 0.15 level, which will increase the level of type 1 error. And that's going to increase the chances that we're going to arrive to a false positive conclusion. Now, like I mentioned before, this is just the first part of a 10-part seminar series that I am going to be offering this term. This is the schedule and the topics of the rest of the 9 parts for this 10-part seminar series. Now, it has been very difficult for me to find a venue like this to do these seminars. That's why I've decided to make the rest of the 9 seminars into YouTube videos so that you all can have a chance of accessing this more easily. And when I'm going to be making these seminars into YouTube videos, I am going to be posting them on a Facebook page that I created. It's called Renaissance Woman. So for those of you who are interested in learning about multivariate analysis or other methods of statistical analysis using R or SAS, if you want to learn about that more, you can feel free to check out this Facebook page or my YouTube channel, which you can access by viewing the videos from this page. And if you like the videos, please feel free to subscribe to my YouTube channel. And thank you for being here with me and listening to me talking about something like multivariate analysis. It is a very useful branch of statistics, but at the same time, statistics isn't the most fun subject. It's actually a very abstract subject, but at the same time, it's a very useful subject. So thank you for being here with me, and if you guys like, I'll be talking to you about other parts of multivariate analysis in my following seminars. Thank you very much.